Hello everyone, welcome to the next session of ANSYS Workbench tutorials. In this session, we are analyzing a beam which is fixed at both the ends for its modal analysis, and then we will consecutively move towards its harmonic response when a load is applied on it. So we will start by double clicking on modal analysis. I'm not changing the material. I'm using the default material of ANSYS, that is structural steel. I'll directly go to geometry, new design modeler geometry. Units, millimeter, XY plane look at. I'll choose rectangle. I'll give it dimensions. See, the length of the beam is 1000 mm and the vertical height is say 50 mm. I will extrude it for say 50 mm. So this is the beam that we are going to analyze. Next I'll go to model. I'll go to mesh and insert method. I'll choose the entire body. We are using tetrahedrons as the mesh. I'm going to insert sizing for this entire body. Here it is given that it is by default 49 mm. So let's give it 10 mm. Update. You can see the mesh over the body. Next I'll go to analysis settings and I will insert fixed support on both the sides. Next I'll go to solution and solve. You can see in analysis settings that there are maximum 6 modes already selected. So we have obtained results for the 6 modes and these are the frequencies that you can see. So I'll just right click, select all, again right click, create mode shape results. I'll go to solution and solve. Now you can see here, because of the first natural frequency of the body, this is how your beam can deform at a frequency of 256.34 Hertz. For the second deformation, which looks like this again, you can see the frequency is 256.34 Hertz again. For the third one, this is the fourth one, fifth one, 1320.6 Hertz, and this is the sixth one, which is again 1320.7. The difference is quite close. So these are the 6 modes that we have obtained. Now next we'll go to harmonic response and drag it over the solution. We'll go to setup and double click on it. We'll first go to analysis settings and we need to choose the range. We are starting from 0. You can see here the minimum value is 256 Hertz. So I can give the minimum value over here, say 100. And the higher range is 1320.7. So I can give this as 1400 Hertz. So this is a range in which I want to see what would be the natural frequencies effect on the body, and when I apply a pressure on this beam, which is what you generally see in your homes. If you have a building and you can see a beam, it is fixed at both the ends and there is pressure applied on the beam. So because of that, the beam has a tendency to deflect or deform. Because of a natural frequency, it will deflect lesser. So you won't see that effect. But if there is a forced excitation on the beam and that frequency matches the natural frequency, any natural frequency of the beam, it can create an amplitude of motion in the body, and you can actually see the beam deflecting the way we are analyzing. So here I'll choose the solution interval as say 40. Next I'll go to analysis settings and insert pressure on this phase. Say the magnitude is 10 megapascal. Then I'll go to solution and insert frequency response deformation. I'll select the entire beam and I want to see the orientation of results as y-axis. I'll go to solution and solve. You can see here the harmonic response of the body. Now we will insert create contour results, and also I want to see the stress because of this frequency. Now you have seen that in frequency response over here, this highest value is obtained as 262.5 hertz and the amplitude is 139.14 mm. So this is 262.5 hertz at which I want to see my equivalent stress on the beam. So this is the equivalent stress, and you can see the points where the stress is generated. Those are the points which are going to resist the maximum deformation on the body. So that's where you see your stress. And those are the points where you will find maximum amount of fatigue, and that's where your rupture can start. Now, in frequency response, you can see this sort of a result. If you are giving a damping to the body, your body will show a better result. Like I have already told you that suppose if you apply a force on the body and this creates a vibration which is equal to the natural frequency of the body, it could be any natural frequency, any mode number. What happens is the body can continuously keep on moving till eternity. But if you want a fixed number of cycles so that the body is usable again, otherwise the body will keep on getting subjected to the load and fatigue and will fail immediately. So if you want the body to move on for longer duration, obviously there should be a damping, that is it should come to a halt. For that you can give a value from analysis settings. You can check here, there is something called as damping controls. Constant damping ratio is 0 currently. If you give the value as 0.02 and just check the solution, you can see here the frequency response, the amplitude has reduced, and we will check what is the frequency. The frequency is 262.5 hertz, but the maximum amplitude has now become 106.42 mm, which is lesser than the previous one. You can see here that there is one peak here and one peak behind at the end, trailing end of the graph. But these points are actually not showing such a big amount of amplitude. Hence, we are not talking about those points. We are discussing about the point where the resonance has occurred, that has led to the maximum deformation of the body. And you can see at the same point there is a phase angle change, that is the body will start vibrating in a different way. Also the input to the body, or rather I would say the natural frequency is one wave, sort of wave. For example, it's a sine wave, and the vibration that you create, say an excitation to the body, is another sine wave. So these two waves, because of the interference, it can lead to a change of way the body is going to deform. Initially, say it was deforming in a transverse direction. For example, you can check here, the first mode of vibration was like this. When you see here directional deformation, you would see the body is becoming axial deformation. The reason is this phase shift, that is causing your body to deform or rather vibrate in a different manner altogether. This is the natural frequency. Had there been no external excitation, no dynamic load on the body would have vibrated like this in this transverse direction. But currently, it has started moving in this direction. You can see. actual direction. So this shift is nothing but the phase shift that you see over here. And equivalent stress, again you can check, its value has definitely changed because you have given a damping coefficient right now. You have caused the body to come to a halt at a much earlier stage as compared with the previous one. Otherwise, the body would have gone a little more amount of cyclic or sinusoidal excitation to it. So I hope you are understanding that modal analysis is about the natural frequency of the body. It is something like you hear a music and you start moving. But that is not a vibrant motion. But suppose there is an earthquake in the building and you can imagine how your body will start moving. That's because there is a forced excitation. That's not because of a light music that you're hearing. So the first example of light music is a modal analysis. That is a natural frequency of, say, even a human body, which obviously has a frequency of vibration. But when there is an earthquake, or say there is a sudden excitation to the chair on which you are sitting, obviously you would feel a different sort of movement, which is something that you are not creating on your own. I must also mention that every organ of our body also has a natural frequency. For example, your heart, your liver, your kidneys, they all have a certain modal vibration or modal value at which they are going to show natural vibration, and that's very less. Hence, you don't feel it in a normal day to day life. But suppose if you are in a journey for a long time, after getting down from the vehicle, you would definitely start feeling that some part of your body is going into a giddy motion. It's moving, it's shaking. The reason is it has maybe been subjected to a forced excitation, which has caused some resonance in the body, and hence your body has shown that sort of a motion. We would see all these type of analysis in vibration analysis, but right now you need to understand what is modal analysis and what is harmonic response. One is the natural frequency of the body, and the second one is because of the dynamic load or an excitation which is created in the body. I hope you have understood the analysis and the concept behind this type of study. If you have any doubts, please write to me in the comment section. Don't forget to like, share, and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.